Okay, so it's my pleasure to welcome everyone to this fourth installment of the DD's workshop, which is on frontiers in monitoring supported decision making for structures and infrastructures. And in this tandem session, we're very happy to have two guests from the US. So the virtual setting has made this possible for us. Professors Mahadevan and Todd, who will be discussing data-driven failure and remaining useful life forecasting. Maybe before I start with the introductions, I will just mention that our tandem series is in the following format. Each speaker gives a presentation for 30 minutes, but we do ask you to note your questions in the Q&A forum, where we will pick them up for delivering these to the speakers. And so it is my pleasure to start with introducing our first speaker for today, which is Professor Sankaran, actually Professor Mike Todd. I am wrong. This will be the first speaker for today. Mike began his postgraduate career in 1996. He was a staff research engineer and then section head at the United States Naval Research Lab, working in the fiber optic smart structures section. In 2003, he joined the structural engineering department at the University of California, San Diego, where he is until now serving as a professor for structural engineering. His research interests are in applying nonlinear time series techniques for structural health monitoring applications. He has a lot of work on nonlinear dynamics, uncertainty quantification with particular link to SHM, ultrasonic waveform NDT, so non-destructive testing schemes as well as, and also an optimization of sensor networks for SHM-rooted performance measures. He has published several works on this, including 400 journal papers and proceedings in these domains. He has been awarded with the 2005 Structural Health Monitoring Person of the Year Award, and he has also received the 2016 Society of Experimental Mechanics De Michele Award, and also serves as the managing editor for the Structural Health Monitoring Journal, which hosts works in this domain. And so I will give him the floor for his talk on the topic, and I think there we will also see some of the domains that I have mentioned in the introduction.
Thank you for that kind introduction, Eleni, and to all of you for the great opportunity to get to join this symposium, this series. I've really enjoyed it so far, so hopefully I won't bring the quality down too much today in this presentation. But as Eleni introduced, my friend and colleague Maha and I are sort of transitioning from some of the big picture framework types of decision-making structures only to show also how, future state is very important. And that's kind of how I'll start today. We've been talking about how monitoring necessitates and enables the decision-making process. We all know that SHM requires a lot of the pieces we've seen, including measuring something, our data streams, and then the very important step of actual data to information analytics. You have to convert data, which usually is not, it's at best just correlated to what we actually want to observe or make a decision about, and find how to extract that correlation through what we can observe. And then, of course, a framework for that. I've always said that one of the things that substantially differentiates SHM from system identification is that SHM actually has to inform decisions, right? It's not just, oh, the parameter is 3 or something like this. You have to actually propagate uncertainty. You have to inform actions to take place, as we all have seen in some of the excellent presentations coming forward in this series. So SHM is very good at giving us the now. What is the current actionable state of our system? And then the next question is, when will the actionable state require the action, right? And that's really where prognosis comes in. It's the capability to predict with uncertainty appropriately qualified the actionable state of the system. And that's what's absolutely needed for life cycle analyses, such as the kind of simulations we saw over life cycles in our last series of conversations. So the way to think of it, maybe very, very simply, is something like this. We have measurements, or I should say, we have features that we are using for our decision making, and that's indicated by some quantitative metric on the vertical axis here. And then we have time, right? And presumably those measures evolve in time as the structure degrades, et cetera. And then there's some limit state. Again, maybe I'm being very qualitative here just to illustrate, of course, what prognosis is, but we have a limit state. And that is, we could define that as failure in whatever way the specific application demands. It could be just time to action, time to maintenance, whatever the desired limit state is and however it's defined. And of course, at some point in this life cycle, we make a diagnostic detection where we can observe what that state is, okay? So we make that detection. And of course, what's important for decision-making, as we all know, is there has to be some uncertainty associated with it. And if you turn your head to the left, you can, I put a qualitative probability density function on that estimate, right? And then the idea in prognosis is we have to then somehow evolve that current state into a future state and take that corresponding uncertainty and turn it into an uncertainty on our prediction of when our limit state will be reached, okay? And fundamentally, this requires models. And of course, the process is you keep making diagnostic updates with your SHM or your inspection, and presumably your confidence increases. And then eventually there's a time where you have sufficient confidence that you might be able to make an estimate on time to limit state, and you still have enough time to take that action appropriately, okay? So that's a rough way of thinking about what prognosis does, but we don't know this black curve here. If we did, there's no need to do SHM or prognosis. We have to sort of estimate it somehow. And that's where either physics or data come in, right? And that's been a big part of the discussion so far. Obviously, as engineers, we love physics when we can use it, you know, maybe a full finite element model or something related. But accommodating that physics knowledge must be a failure or degradation submodel. And quite frankly, it is in my opinion that the physics of actual degradation mechanisms for complex failure modes is very ill understood. We really don't have first order principle physical based models for most failure mechanisms, simply because they're too complicated, or we haven't developed the physics, or they're too non-stationary, or there are just too many phenomena that affect their evolution. Of course, physics-based modeling, well, all forms of prognostic modeling require a future demand model on the structure. You have to know the loads, the environment, usually probabilistically given, of course. And then, of course, you always have to embed uncertainty in that evolution process, that degradation process. Now, that's physics-based. And then there's also data-based. Now, purely data-based modeling of degradation in principle requires supervised learning. The idea is you know something failed, you've seen it at different independently observed states of degradation, and you know how your measurements correlate with the independently observed state of the structure. And that does require a lot of data. And the problem with that for a lot of structures, think of a very high capital asset structure like a bridge or a dam or something, it's very unlikely we're going to have that kind of data. If no other reason, these structures don't fail very often. Now, we might get some bit of a life cycle and see some evidence of degradation from which purely empirical database driven modeling can occur. But there are very few applications where we have statistically rigorous data sets in a supervised sense that take us from birth to death of the structure's life cycle. I would argue maybe in the rotating machinery application space, we are able to have that because the consequences of such failures are not as drastic, and run to failure models in that application domain have been used a lot. So we've built up the power of being able to do supervised learning. But I would argue on aircraft structures, most civil structures, it's impossible to do a detailed supervised learning type of purely data-driven model. And so what we do most commonly, I would argue, are hybrid data-informed empirical or mathematical modeling, where we take some aspects of physics or some phenomenological understandings in physics of a given degradation mechanism. We take our experience, maybe the history of similar structures or the history of a particular structure, and we push all this together into some kind of what I would call more of an empirical type of approach. And that's still data informed and data infused, but it also takes in some ideas from physics. And that's what I'll talk about today. I'm going to talk a little bit about the specific failure mechanism of fatigue, which is an important mechanism in many applications. And this is one that's received a lot of a treatment over history for a lot of reasons, in that it's very common among many different application domains. People have looked at even fracture mechanics inspired. It's one of the more physically motivated ones, at least early on. The Paris-Ergodin laws. You can look at stress strains versus cycles, the S/N approaches like the Palmgren-Minor law. There's the Wöhler, Strohmeyer, Stürzi, Weibel, and so forth. There are stress field approaches, and I'm not here to review those. These are all some that are physics-informed, empirical-based mathematical models of fatigue failure. And what I'm going to talk about today is a phenomenological model that fits in this broad scope of data-informed prognosis in a semi-real-time way, okay, that takes into account a little bit of understanding of the physics of fatigue and crack propagation, along with the fact that we have very limited data. Okay, so this idea is completely stolen from the geotechnical community, where it was observed that landslides, of all things, were associated with something known as a self-accelerated process. And what they noted is that the inverse rate of change of the ground surface velocity on a slope was proportional to the observations of that were proportional to the failure, the sliding of the slope down losing its ability to sustain load and sliding down the hill, causing a landslide. And this self-accelerated behavior is the idea from physics that we want to pull into fatigue. It's been shown applicable to earthquakes, volcanic eruptions, and far more recently to material failure mechanisms. And you look at these three plots of different failure mechanisms where these are actually laboratory controlled data. You see that volumetric creep, crack growth, and fatigue have a very common property, that they have this sort of vertical asymptotic behavior. And that's the self-acceleration. What we see is that the derivative of these empirical processes is always positive. The first derivative is always positive. And as a consequence, the behavior becomes self-accelerating and has asymptotic behavior. So this kind of approach can be modeled mathematically as a surrogate for such accelerating processes, okay? And one such form in general is if you can, whatever you're observing, maybe it's strain rate, maybe it's a measure of crack length, actually, if you can measure that more directly. There are many forms of models. The two most common I show on this slide that observe this empirical phenomenological self-accelerated behavior. And so that the rate of change in the observable is proportional to some power or an exponential law. This is representative of what's known as a positive feedback relationship. And it's very easy to determine failure. A very natural failure criterion comes out of the mathematics when the time rate of change of the inverse of the rate goes to 0 when you reach that vertical asymptote. So it has a really natural, self-consistent definition of failure. Okay, now you may choose to define failure to be prior to that, to introduce conservatism representative of whatever uncertainty you have in the process, but nonetheless, there is a mathematically self-consistent definition. So you can actually solve that simple differential equation and get the form that looks like this. And so effectively solving for the time of failure. When does that vertical asymptote reach its, when does it occur in time? So you actually have what looks like a deterministic form of when time of failure happens. So you have a prediction based on the empirical results, okay? And you can see for different values of a parameter what that might look like. All right, you're measuring this inverse rate. This is your data, P, and the time of failure is some function, if you will, of your data scaled by some parameters of the problem plus the current time. Okay, so this obviously has units of time. This is the general empirical way that this relationship works. And in fact, what people did originally in the last 10 years was they observed, first of all, that if the parameter alpha happens to be 2 based on knowledge, assumption, or otherwise, that this actually follows a linear relationship. And so what people did was just try linear regression, okay? You can actually regress against this parameter K, which is the only unknown. You measure this is your feature. Of course, you know what the current time is, and you can regress on the parameters TF and K. It's basically looking for a projection when the line crosses the horizontal axis in those charts that I just showed you before, okay? So the time of failure is predicted by the negative ratio of the regression parameters, and that's the first representation of how this problem was implemented. So you might think, oh, it may not work here. Oh, it does work. So you see what happens as data accumulate, you make a linear regression and see where your estimate crosses the horizontal axis. So the failure time was here. This is data, and you measure data for some period of time, linearly regress it, and find those regression parameters, okay? So that's straightforward. So as a first cut, what are we missing? We're missing all the uncertainty that inherently comes into this model. You have regression parameters, but a deterministic estimate of T sub F, your failure time, is useless as a decision maker. Because there tends to be, especially in early life, there has to be a lot of uncertainty associated with that. So the first step to this was build an error estimate around that prediction. And it turns out that the error in a linear regression, the two parameters that we're regressing, T sub F and K, the slope factor, are in fact normally distributed if you do a proper linear regression. And so the time of failure becomes a ratio of two correlated Gaussian parameters. And there is available, if you are willing to do some mathematics, so close your eyes for this slide. It's not necessary for the purposes of discussion, but we can actually find a closed form solution for the probability density of the time of failure. It's very complicated, but it's all a function of measurable parameters in your data, okay? And so in this case, we were able to then now compute a probability density function for that T sub F. Not just a prediction, a deterministic point estimate, but a probability density function based on your currently regressed parameters. So you see what the T sub F does over time. It gets narrower and narrower as you become more and more confident, more data is built up over time. Okay, you see it right there. And that's just some snapshots of what those predicted probability density functions are. Okay. And so at some point in a prognostic application, you receive sufficient confidence from that posterior or from that predictive PDF as to when you think time of action or time of failure, whichever that is, you're trying to predict works. And so, of course, we did this on some fatigue experiments where we had a series of these types of tests on a mild steel subject to admittedly controlled testing parameters. And you see the specimen here where we sent it into failure under a controlled seeded crack. So we knew kind of where the crack would happen so we could actually measure it, okay? we were able to bootstrap off a series of experiments to generate appropriate statistics, noise, if you will, that we could then scale up or down to test performance of some of these approaches. And then we compared it to a Paris law prediction, how people would have done this traditionally. Okay, so you could think of two predictions of the cycle of failure. Here's the cycle of failure from Paris law. Here's the linearized failure forecast method that I just quickly introduced. Okay, run a bunch of Monte Carlos and there's the results. Okay, the blue is what the failure forecast method is. The black dashed line is the point in time when failure occurred. The red is the Paris law approach. And you see that this failure forecast method provides far better confidence. The blue curve is predicting far better confidence and better accuracy over the life cycle of the structure. Okay, admittedly a simple experiment, but it shows the power of the empirical approach. Fewer parameters that have to be either estimated or assumed. And this could be studied to see best when the method fails, like when you should sample, how much data before you make an estimate, and even what statistic you should be measuring on the output. Is it the mean of the PDF, the median, the mode? And it turns out that the median is the most robust parameter. This is a lot of plots that basically conclude that the PDFs are sufficiently non-symmetric and have some wide tail behavior that it's much more important to use the median as your most robust predictor from the PDF as the time of failure. And that's all what these studies have shown, that they're the most consistent, most robust predictor, statistical metric. And then of course, one always asks, can you do better? Because the assumption of this linear regression is not a good one. Why not use a Bayesian approach and just estimate the parameters in real time from the data? And that's exactly what the final step was, is to try to do estimation of the model parameters in real time. Because if that alpha parameter as part of the failure forecast method isn't 2, you have some bad model bias. And model bias is usually the killer of any prognostic approach. It's not often the incoherent noise error control. It's the model bias that tends to drive bad errors. And so it's better to estimate posterior distributions, perhaps without making any limiting assumptions. And that's what we tried on these approaches. And we actually compared at different stages of crack growth where that alpha parameter is in fact in the real world non-stationary. Okay, alpha going from less than 2 to 2 to greater than 2 in a real crack, in a real life cycle. And we basically showed that the Bayesian posterior compared to the linear regression, when you have assumption of linearity when it's not there, is of course much better, much more accurate, even over a uncertainty quantified linear regression in real crack cases where the parameter is non-stationary throughout life cycle. So our posterior PDFs estimated the time to failure with much better confidence and fewer problems. Okay, so this is just one demonstration in this quick presentation of one model form of prognostic use that feeds a decision-making process. Okay, these are just some conclusions about the specific approach, but perhaps more importantly for this series, is to go back to some of the questions raised by this. Can data by itself be used only, or can physics be used? And I think both of those are no at this stage. Data by itself can't be used because it really can only be done in most applications with a supervised learning mode, right? And we just don't, I'm not convinced we have enough actual failure data to do it. So, and because our lack of physical knowledge precludes a lot of first principles based modeling, the kind of approach I just showed, where some physical principles coupled with some data hybridizing the approach to make predictions of the future, I think are the sort of the appropriate way to advance the field and push prognostics ahead, such that it can feed the kind of life cycle assessments that a lot of our excellent speakers have been talking about so far. So I think that's a good place to stop. I think I did it in about 25 minutes, Daniel. So that's what I was hoping to accomplish. So thanks very much.
Great. Thanks, Mike, for keeping time, actually more than that. So that gives us afterwards a lot of time for discussion, which I think there is also a lot of material for discussion in your excellent presentation. So I'll just go on and introduce the second speaker. That is Professor Sankaran Mahadevan. He's with the Vanderbilt University in Tennessee, USA. And he has more than 30 years of research and teaching experience in uncertainty quantification, risk and reliability analysis, machine learning, structural health diagnosis and prognosis, and the decision-making under uncertainty. Importantly, he has applied these methods to a large variety of structures, materials, and systems in civil, mechanical, and aerospace engineering. And on a personal note, I remember when I was a relatively young, new PhD student attending a conference where I met Professor Mahadevan for the first time, and I was very impressed by how he, because I knew all this, well, I had heard of different theories, but I actually saw how he used the theories for real life applications in a meaningful way, and I think it was really at the time, yeah, quite an impressive presentation for me. And then 15 years, 20 years later, still or even more impressed by all the work he has done. So he has been at the forefront of academic research in the past 10 years on the digital twin methods for different types of structures, aircraft, rotorcraft, chip structures, additive manufacturing, research funded by Air Force, US Army, FAA, NSA, and NIST. And I think his talk will be a lot about this topic today. And maybe I should also mention that he's a managing editor of the Journal of Risk and Uncertainty in Engineering Systems, and also has served as a general chair of several prominent conferences, one of which I attended, and it was very perfectly organized. So Maha, thanks a lot for giving this talk and discussing with us, and we look forward to your presentation.
Thank you, Daniel. That was a very kind introduction. I really appreciate your kind words. This is a mutual appreciation club. Of course, I have been very impressed and inspired by some of your works also that are related to my work in terms of the Bayesian networks and so on. So we have a lot of common things to share. I assume you can see my slides.
Yes, looks good.
So I can promise you right now that I will not be as good with time as Mike was. I always over prepare for these things, so I might have to let's see, hurry and keep my time. So I'm going to particularly focus on digital twins. We had Michael Faber last time talk briefly introduced the concept of digital twins. So I'm going to go deep into that. And the idea being that it's not just a single, any structural health monitoring or diagnosis and prognosis does not operate in isolation, but it's really in the context of the entire system and the environment it's operating. So there are lots of things that affect diagnosis and prognosis. And so how do we account for all these things? And especially what are the implementation challenges and in scaling up to real size structures and systems? That's what my focus is going to be. Just to very simply introduce the idea of a digital twin, which is a virtual representation of a physical system. And of course, there are data interconnections going both ways, from the physical to the virtual, and then from the virtual to the physical in terms of decisions and actions. And this virtual representation, or a computer model in many cases, or database models, It consists of all of the information about the system from design to manufacturing, its properties, operational history and health history. Everything is put in together so that the virtual representation evolves as a twin of the physical system and keeps getting better and better at representing the actual system. And this is done, of course, with updating of the virtual model with data about the physical system. Now, why we want to do that is we want to be able to manage the risk of that individualized, not a fleet of structures or assets, but really for that individual structure, because each one has its own unique history and we want to be able to capture that. And therefore, we want to make decisions with up-to-date information. The motivation for this also comes from reducing cost, because if you have the prior physics models and then also with new data and you're updating your models, you don't have to do as much of testing or inspections as without models. And then also there's risk management because of monitoring and control. Here is an example. 20 years ago, we did this for a fatigue study where we showed that if we were doing only tests, we would need, we would need a lot more tests, and then still the confidence interval or the uncertainty bounds would be quite high. Whereas we could achieve, just like what Mike was showing, our uncertainty reduces quite a bit. And so we, in fact, showed in that case 50% reduction in our testing cost. So this is one of these important motivations of these hybrid models, which leverage both physics information as well as the data that you are obtaining. The things that I'm going to focus in this presentation are, first of all, in the context of implementation, the issues of information fusion, since the information is coming from many different directions and in different formats. How do you manage the uncertainty? And then how do you handle the computational effort for realistic systems? So I'll start with some general implementation considerations and then dive deep into the type of computations that this audience would be interested in. First of all, when you are trying to build a digital twin, you want to be very clear about what is the targeted outcome you are intending to achieve, whether is it cost reduction, risk reduction, maybe improving the efficiency, reliability, and so on, resilience. And then you want to make decisions for that particular asset. You want to decide what the scope and the levels of fidelity would be, and how you specify the physical asset, how do you construct the virtual. There are a lot of details that really are quite, it requires actually a team to put it together. If you look at here, the kind of information, there's three layers that I'm showing. At the bottom is all the types of information that you are getting, either is expertise or data in terms if you are some customer serving service, then transactional data, sensor data, operational data, and commercial business data. There is one layer of data, and then there is a layer of models that do various kind of activities, such as maintenance decisions, life cycle management, and so on. And then there are these business outcomes, such as cost reduction and regulatory requirements meeting or growing the revenue of the company and so on. So there are these three levels. And as you can see, there are lots of different data models or data sources and the computational models. All of them have to be put together. So this is not a trivial task at all. Going a little bit into the scope, you may not be able to construct the digital twin for the entire system in one shot, but you may have to do it in a modular fashion, stage by stage. And there are, and the level of fidelity you want, it depends on what kind of decisions you make. In some kind of decisions that are low consequence, perhaps you can get away with low fidelity models. But if there is a very high consequence decision, then you may need a lot more fidelity in your digital twin. So you would be doing a balance between cost and complexity and the outcomes. if you have existing processes for data collection and modeling and so on, and how much you can leverage that would certainly help you in building this digital twin. And so if you look at this on the right hand side, in terms of the data, the measurement that is coming in, so you have the physical reality, which you are measuring with whatever measurement techniques you have, and then you have some observations. And then you have interpretation of that in order to feed into your models. So there are a lot of uncertainties that come in this every step of this process in terms of the data. Now, if you were to this cartoon that I showed earlier, if you were to look at the details of the various things that are going on, the system is operating, and then you have measurements, and then you have interpretation. So that's all in the physical space. That interpretation then, of course, borders into the virtual space, where you're doing model updates and so on, condition update, and doing prognosis, basically analysis, and then you're making decisions, and then that is communicated back to the physical system as action to be done on the system, so on. So this goes on. So by the way, there is just a recent review paper that came out on this digital twin, the various elements, and how to consider all these different elements in the implementation. So some of the challenges implementation, first of all, when you have you're building digital twin for systems, the communication is a big challenge. Of course, you have people from different disciplines. They would use the same word, but probably mean very different things. And some people use buzzwords just because they like them. You will hear the word uncertainty quantification thrown around quite a bit, but you might, if you drill down deep into it, all they might be doing is just doing a simple statistical mean and variance calculation from some data. So there might be confusion because of communication and use of non-standard terminology. There is also a need for standardization. If you are especially bringing in data from many different sources to build your digital twin model, how the data is interchanged and what format the data is available, and so interfaces. Right now, a lot of the digital twin implementations are done in-house, so you don't know how they are doing it. So standardization is another major need in this regard. So that you can use commercial off-the-shelf systems and put them together. Of course, the organizational culture makes a big difference. Different stakeholders will have different competing objectives. This technology maturity is another one. You may have great computational models and excellent measurements, but if you don't have a good for example, if you're trying to use the internet to transfer the data and do the communications and transfer the decisions, you have to have a very strong supporting infrastructure and technology that is mature enough to support this type of work. And then, of course, you need verification and validation of your models, and not just the individual physics models, but really of the whole digital twin, how the whole thing is integrated. And so that you can quantify, just like what Mike mentioned, the model bias and variance or uncertainty in the prediction. So this is an implementation that I'm going to start with the ship structures, marine vessels for American Bureau of Shipping, ABS, which takes care of these various activities that I mentioned in the previous slide. And I'll go a little deeper into this for marine applications. So the motivation was to support diagnosis and prognosis in a way that integrates all of the available data and models to therefore reduce the overall inspection, maintenance, and repair costs for these vessels. So in the case of diagnostics, we are looking at anomaly and extreme event detection, and also monitoring the damage accumulation in the vessel based on all the operational profile. For prognostics, we are looking at two things. One is fatigue, and then the other is corrosion damage. First thing is to notice the architecture of the digital twin, which of course consists of many different data models and computational models. If you look at on the picture on the right hand side, you have sensor data, maybe on board, or some inspection. Then you have all the operational history and environmental data and the geometric models of the structure. And then all this is being fed into some databases from which the various models, engineering models, are doing their calculations. And you might have some low fidelity or high fidelity depending on the type of decisions you make, and then leading to various types of decisions. Oops. So this is quite a complicated exercise of putting all these things together and have them work end to end smoothly. In our case, what we were looking for is also doing prognosis to identify early enough some emerging risks due to the various operations of the ships and estimate the damage accumulation. So this is work on that is being reported in a special issue in RESS on this marine vessels. So some of the elements are, first we look at the, if you look at this particular vessel, let's say, that went from Europe all the way to China, then you have this history of the track that it went in based on its coordinates. Then you look at this Met Ocean hindcast data, so you find out what the wave conditions were during this voyage. And then based on that, you also have the thickness measurements, let's say due to corrosion in the vessel at various locations. Then you feed all this data into the computational model, such as a hydrodynamics, a seakeeping model, which then translates to loads on the structure. And then you do a full finite element analysis to get the stresses. And then from that, you go on to calculate fatigue damage accumulation, and then prognosis, and then support these various types of outcomes in terms of damage accumulation and remaining useful life and so on. And then support decisions for risk management and also availability of the ship, let's say for the next voyage. Does it need to be repaired? How long will it take before it can be put in service again, and things like that? Or how much can I extend its life for future missions? So in this case, we built the digital twin mainly up to this point, which is just to do diagnosis and prognosis. And then the decisions were done manually by the operators. So then I want to drill further and saying, well, how about the decision making also being part of this digital twin work, where you have this particularly we have been using aerospace systems to demonstrate these ideas, where you have, let's say, aircraft or rotorcraft flying these missions from which you collect all the data, and then you have the damage diagnosis and then damage prognosis, and then based on that, you optimize the next mission and so on. So some of the details, the computational elements are probably very familiar to many of you. You start with multiphysics models of the aircraft or rotorcraft. You do sensitivity analysis and surrogate modeling because you want to have the any uncertainty quantification or diagnosis prognosis techniques will necessarily involve many samples, like using Monte Carlo samples. So you will need some kind of surrogate model to accomplish that in a reasonable amount of time. Then you fuse the information using Bayesian estimation and then quantify the uncertainty in diagnosis. Similarly, in the prognosis, you use the forward problem and you quantify the uncertainty there. Also coming from the models that also have their own uncertainty. So all that has to be accounted for. And then you do this optimization. This optimization now could be of various types. So the decision horizon becomes very important. You might need sustainment decisions such as inspection, maintenance, and repair. There the decision horizon is fairly long. Maybe you could take a day or two or maybe a few days to make that decision. On the other hand, you might want to do things like mission planning. Okay, this rotorcraft had to go on a next mission. What type of mission is it capable of doing given its current condition? Or what type of flight profile it can support without growing some damage and so on. And the flight maneuvers would be, even during flight, your decision might be like within a second. You have to make a decision which maneuvers to take so that the damage doesn't grow any further, and so on. So depending on the decision horizon, your digital twin will have to have the corresponding computational speed versus accuracy trade-offs. This is an important issue that comes up. In fact, for one of the first digital twin work that I did with the Air Force commander who addressed us at the kickoff of the meeting, he said, well, we have tons and tons of data that we have collected, but we don't know what to do with it. And any decision that your digital twin makes has to be made within 20 minutes. Right now, it takes us 2 weeks to assess the condition of the aircraft and make decisions. We would like to bring it to within a day and perhaps even within half an hour so that we can quickly move these things through. So that was the challenge that we were looking at. And, if you look at the information, we've already looked at this. There are many different sources of information, and all of these are coming with different formats, and different levels of fidelity and different time scales. And the uncertainty itself comes from many different sources, such as the variability and model uncertainty, data uncertainty, and then the input uncertainty, and so on. So you have multiple sources of uncertainty and multiple heterogeneous sources of information. This is the scenario in a real system. So how do you aggregate all of these uncertainties? It becomes quite complicated. It's not a straightforward square root of sum of squares anymore. And so the system assessment is obviously affected by all these uncertainty and information sources. So we need a systematic approach for this kind of uncertainty quantification, which can then inform the decision making. So I'll walk through three examples and then set the stage for the computational methods that we have looked into. This was the first digital twin work, actual formally named digital twin. We had done some work before that as precursor. First contract by the US Air Force for an aircraft wing. This was for an F-15 aircraft wing. So GE was the lead. They integrated. The Vanderbilt had all the probabilistic computations, and Lockheed had all the aircraft CFD and FEA analyses and so on. And so we were fusing physics models, the mission histories, inspection data, and doing damage growth. In this case, it was fatigue crack on the wing, damage growth prognosis. Of course, we had to build surrogate models. We used Gaussian process or Kriging surrogates of the CFD and FEA physics models. And we incorporated uncertainty sources from the physics model, the crack growth model, damage diagnosis from the measurements and so on, and the loading variability. So how we integrate all of this is using a Bayesian network. So here is, for example, a dynamic Bayesian network which evolves in time. So question is, how feasible or affordable is this for a realistic structure? So that the computational efficiency and scaling up became a major stumbling block for this type of work. This is a simplified example where we did academically, and then the GE and Lockheed did it for actual F-15 wing. So for this, we want to be able to have results like this, where as the mission there is a mission, and then there is an inspection at the end of the mission, and then second mission, and so on. And you want to be able to predict how the crack might grow, and then the uncertainty bounds on that prognosis. So these are the type of results we were trying to achieve for the decision makers. I'll get a little more detail into this dynamic Bayesian network in a minute. Another example, which is we are doing it actually now for the US Army, is for rotorcraft or helicopters. In this case, we do two things. One is mission planning, and then later on I'll talk about maneuvers within a mission. So in this case, we were looking at optimizing the flight parameters, let's say horizontal and vertical velocities at each flight phase, in order to complete a mission and minimize the stress on the on this component, which is the mast on which all the blades are mounted, the rotor blades are mounted. And so the loads are coming from a computational structural and fluid dynamics model, and then a FEM model does the stress and strain analysis. And we were looking at a particular type of degradation where there might be reduction in effective cross-sectional area due to damage. And so supporting diagnosis, prognosis, which includes, of course, model update, and then optimizing the mission profile. In the case of within a mission, this is the thing that we are doing right now, what we call damage adaptive maneuvers. So suppose you have a rotorcraft in a battlefield that has been hit by some enemy fire, and it has some damage, and you want to be able to complete your mission and return to the base safely. So how do you adjust your maneuvers in such a way that you complete your mission but without growing the damage further, which means what? You just adjust your maneuver so that the load is redistributed so that the damaged area does not get affected further. So you can see the all the data, the sensors that are we were looking at this fuselage section, and the sensors are mounted here, which convey the information about the damage, and then using the models, integrate them through the Bayesian network to do diagnosis and prognosis, and then optimize your operational maneuvers. For example, if you have this, these are two trajectories. There is a red one and there is a blue one of the helicopter. And as it flies two different trajectories, you have different load profiles, which of course affect the stresses on the various structural components. So what you want to do is, let's say you want to have a trajectory that will safely complete the mission. So let's say you have a mountain here, and so you have to fly around the mountain. So you have some specified trajectory. What we do is first we learn what kind of maneuvers are needed, the various types of maneuvers needed to follow that trajectory. This we do using reinforcement learning. And then using those maneuvers, then we can calculate the loads on the aircraft using this ARCAS CFD and FEA model. And then based on the FEA model, we can get the stress and damage growth, and then we do it in iterative fashion to see what is the most optimum trajectory that will minimize the damage growth. So this is the damage adaptive maneuver work. So the digital twin is now supporting, and imagine this decision has to be done very, very fast. So the three examples I showed you have three different decision horizons. Now let me get into the computational elements. Many of you might be already familiar with quite a few of these. First of all, there is information fusion, and this is being done using a dynamic Bayesian network. Of course, there is sampling of the uncertainty, either for prognosis or for model updating and parameter estimation and so on, using MCMC or particle filter type techniques. The physics model, the full fidelity physics model might be very time consuming to do. So quite often we would resort to reduced order modeling or multi-fidelity models to support our work. In many cases, even that might be too expensive. So we would end up doing surrogate models. Either surrogate models that are purely based on the physics model, and many of us have done for many years these types of models, polynomial chaos, Kriging, Gaussian process, radial basis functions types models. Or you might have data-rich environments too, which we are doing a couple of projects right now, where you are able to build a purely data-driven model such as ARMA models or support vector machines, deep neural networks, or recurrent neural net for time series problems, LSTM type models. And in some cases, similar to what Mike said, you might have physics-informed machine learning or hybrid models are possible. In surrogate modeling, there is also the question of adaptively selecting the data to train your model, what is referred to as active learning. but we are actually looking at some problems right now where the dimension is very, very large. We have a project going on with Mitsubishi on building digital twin for aircraft fuselage as well as for the engines components. And there we are looking at very high dimensional output, and they are not sure, it's not like a one particular hotspot where you want to monitor the response or damage, but it's depending on the flight profile, you could have a variety of hotspots. So they want us to build a high dimensional surrogate model. So we are looking at how to do dimension reduction either in the input and in the output, and then build these effective surrogate models. This has become a pretty big challenge in recent years. So drilling deeper into each one of these elements, of course, Bayesian network, a simplest way of saying this, it's a graphical representation of a joint distribution of a lot of variables using marginal and conditional distributions. And if you want any particular marginal distribution, you integrate out all the other variables. And if you have new data, you are updating. This is, of course, using the Bayes theorem. You're updating not only there, but then the information passes to all the other nodes as well. If it's that's a static Bayesian network. If you are dynamic Bayesian network, then you also have multiple copies of this network over time. And then there are also these transition probabilities that come into play. So for diagnosis and prognosis problems, the dynamic Bayesian network is what is appropriate. Now, some of the previous work on Bayesian networks and the commercial software have mostly considered discrete events and their probabilities, whereas the kind of applications that we are interested in, of course, many of the variables are continuous and some are discrete, so you have to have the ability to handle mixed set of discrete and continuous distributions in here. So the inference in the Bayesian network can be done either using Markov chain Monte Carlo sampling for typically adopted for parameter estimation, whereas particle filter is probably what you would use for state estimation, where you propagate the particles to a next time step, look at the observation, and readjust the weights and resample, and then the updated particles are then propagated to the next time step, and so on. Both of these are computationally expensive. Neither of them is cheap. Particle filter might be a little less demanding than MCMC, but still, you cannot use the original physics models to do that, but you'll need the surrogate model. One option also is that if you can justify this, Gaussian-based approximations, such as multivariate Gaussian or Gaussian couple or mixture, or Gaussian-based inference techniques, instead of doing a full-blown particle filter, you might do things like Kalman filter or its variations. The reason why we would pursue that is because if you use Gaussian approximations, you get analytical solutions, which makes the computation very fast. So in the case of our work, we have some variables that are Gaussian, some are non-Gaussian. And so you might convert them all to a Gaussian space and then do these analytical approximations. So coming back to this crack growth prediction of this rotorcraft mast, and you have here, you have the loads being monitored, and also the inspection is telling you, let's say, what the damage condition is with which you are doing the prognosis. Now, even this Bayesian network is, first of all, has multiple layers, many different models coming into play. There is a finite element model here, there is the crack growth Paris law parameters here, and so on. So you have situations where you have a multi-layer Bayesian network. So one of the things we did to really make the computation scale up to high dimensional problems is, first of all, convert this multi-layer Bayesian network to a two-layer Bayesian network. How do we do that? So suppose you have these three layers and stochastic variables, then you can convert this C0 to C1 in this manner, where C1 becomes a deterministic node where you introduce what is called an auxiliary variable. based on the probability integral transform, and using this auxiliary variable, and then this becomes a deterministic variable. Once this is deterministic, then you can collapse it into a two-layer network. And similarly, if you have a network like this, multi-layer network, each time you have these intermediate stochastic variables, you can use an auxiliary variable to then collapse them into a two-layer network. So you have two of these intermediate variables, so I have two auxiliary variables introduced there using this probability integral transform. So we applied this to this crack growth Bayesian network that I showed you before. And so you have so many layers. Some of them are, of course, deterministic, which are just intermediate variables. And so you can collapse them into something like this, but it's still a three-layer. So when we introduce auxiliary variable, it brings it down to a two-layer. Once I have this two-layer network, what I can do is I can build an unscented transform to connect these upper layer to the quantity of interest, and then use an unscented Kalman filter, which accounts for the nonlinearities. But of course, it's still applicable to Gaussian. So if you have non-normals, then you have to use equivalent normal transforms before you use this. But this is something. So you can have a very fast and approximate inference on these multi-layered Bayesian networks, which is something you will encounter in common digital twins. The other idea is also when you're building surrogate models, if you have a very high dimensional problem, you have, in this example, you are interested in stress intensity factor at this location, and you have many input variables, and finite element runs are sparse. Right now, we are doing this project for Mitsubishi, where they have given us 81 finite element runs, and they have asked us to build a very high dimensional surrogate model from that for diagnosis and prognosis for a fuselage panel. So how do we even build with so many input variables? So we use, of course, sensitivity analysis to identify the dominant variables. But sensitivity, you only have 100 finite element runs. So how do we do sensitivity analysis? So we developed this idea back in 2014 on this, what is called a stratified sampling or modularized method for sensitivity analysis, where we divide up the range into equal probability segments, and then we calculate the variance within each segment, and then take the expectation of that as an approximate estimate of the first order index, and use that to identify the dominant variables and build the surrogate model. And we extended this idea to also same thing for a Bayesian network as opposed to a deterministic model. In this case, we are also able to include not only aleatory but also epistemic uncertainty sources. So when we did all this, for the same problem that I was showing you for the aircraft wing, this is of course an academic example we did in at the university, and then GE implemented this for the actual F-15 aircraft wing. So you have here this multi-layer network. So we do the fast sensitivity analysis and then collapse the BN into a two-layer network and then apply unscented Kalman filter. So first, the sensitivity analysis removed a lot of the other variables that were not dominant, and so only a few were left. And then the collapsing into a two-layer network and applying the UKF. So you can see here something that even with surrogate models took us 10 hours to do to begin with, this sensitivity analysis, and then the collapsing and doing unscented Kalman filter brought it all the way down to 1 second from 10 hours. So now we are talking, scalability. So when GE and Lockheed implemented this for the F-15 aircraft wing with a very high, million degrees of freedom, very detailed finite element model and information fusion, and doing this type of prognosis, they accomplished that within 20 minutes. So the commander wanted us to do it in 30 minutes, and we got it done in 20 minutes. So that's what I'm saying, the power of these various computational algorithms to speed up. And yet, of course, we had to validate that with the actual data to show that the models did not have a large bias. So we are now applying this thing also to smart manufacturing. This is work funded by NIST. I see that I have overshot my time, so I'll just quickly show this example. In this case, the turning process, the tool is wearing, and so we want to monitor that, and then advance the tool so to keep the diameter at the required length. So again, we build a dynamic Bayesian network to accomplish this, and without the control, we would have the diameter would have continued to grow. This is what was specified to us by NIST, that we need to have it within this bounds, and by this monitoring continuously and doing the prognosis and control, we were able to achieve a very, very high accuracy in the diameter. And now we are applying this to additive manufacturing, again also sponsored by NIST, where you have the infrared thermal camera and the profilometer. They are measuring the temperature profile and the surface roughness. And first we do process parameter design, similar to what we did in terms of emission planning earlier. Now we're doing the process optimization that will minimize these surface roughness and porosity and so on. Then we also do process control during the process, monitoring it, and therefore doing diagnosis and prognosis, and then adjusting the process parameters to make sure that the quality of the product is what we want. So in doing so, of course, you have many different models, especially in the case of a metal additive manufacturing, many different models that need to be integrated. And the data, this is also a data rich environment where you have a thermal camera that is getting the entire thermal profile. So we have built various kinds of machine learning models and hybrid models for these different scenarios to achieve so this is a digital twin for manufacturing process control. In fact, the original digital twin, the very first 2003 paper by Michael Greaves, was actually for manufacturing process control. So we've kind of come back a full circle on this and doing it for additive manufacturing. So this is my concluding slide. So the kind of things that I have highlighted today is about information fusion in terms of heterogeneous data of different precision and cost, and models of different complexity, accuracy, and cost, and the multiple source of uncertainty, and how to come up with computationally efficient strategies that can scale up these techniques to real applications. And so the dynamic Bayesian network approach that we have adopted with all the efficiency strategies both facilitates the forward problem of uncertainty in prognosis, uncertainty aggregation, and also the inverse problem of decision making. Two levels. One is the uncertainty reduction, and the other is then actual decisions with the digital twin, such as sustainment or mission planning or control during the mission or process, and so on. We are currently expanding this idea of digital twin now to two very large scale projects now. So far it's all about individual components and parts within systems, but now we are doing one for the power grid system in the US, where you monitor the power grid fluctuations, the demand and supply fluctuations on a minute by minute basis, and you are making decisions. So there is diagnosis and prognosis. So we are building a digital twin for entire sectors. And another large project that we are doing is for aviation safety, looking at individual flight safety at various phases of flight, and also sector-wide safety in terms of conflicts, especially as the air traffic grows. You have a lot more density in the airspace. So we are doing that. And the third one is, as I mentioned, the Mitsubishi project on building digital twin for aircraft fuselage panels as well as for engine structure. So there is a lot of work to be done in pulling together all the various elements in order to actually realize the promise of these data-driven models for prognosis and decision making. And the data-driven models get challenged quite a bit when you have large systems with multiple streams of information and many different types of models, and the decision horizons are very short. Thank you so much for your attention. Again, apologies for going over the time limit.
At least you gave us a warning, but it was actually very interesting. Maybe then to thank you both for the great presentations. I wonder if we could maybe start with a question for Mike. In what you showed, of course, there is this value of empirical models, which I also agree is quite significant. But I'm wondering in processes that extend to higher dimensions. And so, for example, maybe you have multiple components and therefore multiple elements that have to follow some sort of law. And maybe these, let's say, structures of multiple components are observed with a monitoring system. And really the way in which you can connect monitoring data with these processes is through a model that couples everything together. What happens in that case? Is the complexity impossible to tackle, or are there ways around this?
No, I think you're describing one level more sophisticated in this empirical hierarchy in terms of what architectures can be applied. And you're absolutely right. These kinds, I still think it's going to be somewhat one of these sort of hybrid empirical statistical models based on what data you have collected and in the past and some prior physics or other knowledge, because I don't think the physics of a full forward developed problem is going to be there the more complex you get because of the exponential increase in the complexity. So it depends
on building maybe more complex and possibly coupled models of these
I think it has to. I mean, Matteo, for example, asked a good question in the panelist that's related to your question more generally. You know, where should progress be made? Is it more in collecting data? Is it more in physics understanding, or is it more in just really strong empirical models with well quantified uncertainty and so forth? And I guess the quick answer to that question that Matteo raised was, to me, those three areas come down to what I think is easiest short-term horizon versus long-term development. I think physics is the longest term. I think it's just, we've reached a point of we don't have enough information to develop physics-based principles for highly complicated systems. And why is that? Because of the second highest priority, which is we need more data. We are now able to collect data. However, I still maintain the challenge I talked about in my presentation. In so many applications, we'll never have access to data for failure. Either failures don't happen, or there are legal issues, liability issues that'll keep us from getting access to data. At least in the failure stage. That doesn't mean we can't collect more and more degradation, early stage life cycle data. And that just begs the question that we should do more to show the business case. And that's what VOI analyses can do, to show why people should invest in life cycle monitoring at the design stage, get structures instrumented at the beginning so we can collect this data. And then my final point would be to take us to the top level, which is what we can do now. I think fastest is what you just are asking about. We have to look for increasing the complexity of empirical and statistics-based models on complex structures to start facilitating making the predictions. But that's just my opinion.
Yes, that's a good answer.
But maybe if I might follow up a little bit on that. And I was working on landslide monitoring at some point and trying to predict the accuracy of landslide monitoring. So we used those models that you showed, and there, I mean, the physics-based models are so complex and that you really cannot use them in many places. But when you showed that you compared with the Paris-Erdogan type of modeling, which is, okay, it's a simple model, but it has some physics, partly empirical, partly physics-based. I was wondering that, so what I understood, you advocate kind of the use of purely empirical model versus this Paris-Erdogan. Did I get that right? And
well, I don't think I
always tell my students that if I have a physics-based model that, even if maybe it's not perfect, but at least, I have some background. Typically, I would prefer that. it allows to extrapolate to other situations, etc. But you seem to have advocated the opposite.
No, I think the way I would answer that is the uncertainty in the parameters of the Paris-Ergonon physics space, which just comes basically from linear fracture mechanics. And one could argue whether cracks really obey linear fracture mechanics or not. And it turns out they do during the middle of their life cycle. They don't early and they don't late. But it was more about that the empirical model that the failure forecast method has fewer parameters and it manages uncertainty better. And the fundamental physics that was infused into the failure forecast method is that it has the self-acceleration feature. And so there is a little bit of physics. It's just not as detailed as the fracture mechanics physics that was infused in Paris-Ergonon. So I guess it's just that there's maybe less physics, but there's enough physics that it has the right trend, and the parameters uncertainty is better controlled and modeled and understood.
Maybe I can transfer a question from the Q&A for Professor Mahadevan. The question is, you have described applications of digital twin to naval and aerospace structures, and what would be the challenges of applying a similar framework to civil structures, in your opinion? Smart buildings.
Yeah, so in fact, for smart buildings, I'm just reminded there is a colleague of mine at Georgia Tech who's actually doing this, building a digital twin for smart buildings. So Olivia is the first name. I'm missing the last name. In fact, we are both, she and I, we are both on this digital twin committee in AWS. So we found that, in fact, that is the answer to your question as well, which is that the basic elements are the same, right? You have the data and you have models, and then how to put them together and support decisions in a meaningful way. So those elements are the same. The challenges that I laid out are in fact the same in terms of communication, standardization, and verification, validation. All those things are the same. Where the differences might be is in terms of the actual amount of data available, the quality of data available to inform your diagnosis and prognosis. So, for example, in fact, even we did some work on this smart buildings, such as temperature control. This is a common example that everybody does in terms of monitoring and controlling the temperature within the building and so on. So the question is, the quality of the data also becomes important. How accurate is your sensor in terms of giving you the right information that you're making the right decision? I'll give you an extreme bad case of sensors. Now, we have these sensors for measuring degradation, strain, let's say, on the aircraft. When I was doing this Air Force digital twin project, in the lab, the sensor has 98% reliability. You put it on the aircraft, the sensor reliability drops down to 23%. So, so you can imagine how this is I think one of the biggest bottlenecks in realizing these visions of prognosis and decision making with the data is that the sensors are still not at the level where our computational models and all algorithms are able to do. So sensing is one big challenge. And I hear from my colleagues who work in smart buildings and smart infrastructure that this is one challenge. And then the quality of the data, and then the data transmission bottlenecks. There is a lot of bottleneck in terms of data transmission. So these are some of the challenges that I'm hearing about in terms of building infrastructure.
Maybe a question to you, Maha. I'm not sure if I understood correctly. For the cases of the wing, what is the kind of information? Is it inspection-based information that you're offered?
Yeah,
So
there are. In that case, in that wing case, the only information we had was inspection.
So approximate location orientation of the flow, and then of the crack, let's say, or depending what the flow is.
Yeah, so you have, of course, now in more modern aircraft, we are putting sensors,
Yes,
strain gauges
that's
and
why I
so
was
on.
wondering if,
But
and
this
my
was an
question,
old aircraft that was given to us for actual demonstration, so which didn't have onboard sensors, especially strain gauges. So it was the only information we had was periodic inspections and maintenance logs and so on.
so I was wondering exactly for the case where you have maybe sensor information, like strain information, which is dynamic, and you require an elastodynamics problem, maybe solution. Do you think it valuable to use physics-based reduced order models and not necessarily surrogates such as Gaussian processes and so forth, so that you can capture the measured quantity in a better way? Or would you still go with
Yeah. So actually, this is a very relevant question. So we addressed this issue for an AFOSR project, where we started with this reduced order, dynamics models, because that's what we could start with. But then the issue is of also the physics models having this model discrepancy. So when you're doing the Bayesian model updating, you also update the model discrepancy term. And so there, the question is, the model discrepancy only applies to the place where location where you have measured. But what is the discrepancy at an unmeasured location? You don't know. So we had to actually develop neural network models to do the extrapolation for unmeasured locations or unmeasured conditions. So our model ended up being a hybrid, like Mike said. So you
Yes,
have
I
the
think
physics-based models plus hybrid models for particularly the model errors in our case.
And even beyond extrapolation, I assume also for modeling the discrepancy, this deep learning or neural network term would help.
Exactly.
Yeah.
Can I ask something maybe that is related?
Go ahead.
Great, thank you. Great talk, both Maha and Mike. Thank you for this. So I have two related questions to exactly what Eleni asked into your presentations, and for both of you. My first would be, we saw a number of different modeling approaches, right? And we can of course start from a high fidelity model. We do a series of approximations, then if we want fast computations or affordable computations, and we end up in a simpler model that validates some data. And then there is another approach, right, to directly start. So if we know this from the beginning, right, can we start from a simple model that also validates some available data? And just a general discussion about this in your opinion, right? What's of course and the best approach perhaps we could take. The problem I think with this is that at the end we want to show what's the effect of our models in our decision support. And if we go through the high fidelity route and then we do dimensionality reduction and other things, right? Then is this justifiable to invest all this time and energy into this? Well, at the end, we have a 2-layer Bayesian network, and we update that. And my second question is about this bias in the models, or the model discrepancy, which I also don't know exactly how to address in a probabilistic framework, in the sense, if we know the model discrepancy and the bias, we can just adjust for this. And if we don't know it, then then what can we do? So any comments or suggestions?
I'll go first, and I'm sure Mike also will have his thoughts on this. So I'll very briefly address your two questions. One is what level of fidelity should we have? Should we start with a simple model or go for a more complex? So this one of the comments I made was this decision depends on several things. One is the kind of decision you need to make. and the decision horizon you have. Do you need to make the decision within a second, or you have minutes or hours or days to make the decision? So obviously the simpler models will be faster to run than the more very high fidelity models. So the decision horizon, the kind of decision, meaning the consequence of the decision, is it a high consequence or is it low consequence decisions, that will matter. And thirdly, how much data you have even to build either a simple model or a very complex, let's say, neural network model. That will depend on how much data you have. If you don't have much data, obviously you cannot build a model with lots of parameters. So it will depend on the data availability and the complexity, the decision horizon and the consequence of the decision. All of those things will factor into deciding what level of model fidelity is appropriate for your use. The second question you had was about the discrepancy, how to handle that. So typically, because you would only be measuring structural response or damage or some information at a few locations. So if you go by the typical model discrepancy route, you would be able to estimate the model discrepancy in those locations, but all the other unmeasured locations or unconsidered inputs, you don't know what the discrepancy would be. So so the thing that we have done in recent years is actually take all that information, go all the way back to the model form, the governing equations, and find the errors in the governing equations, because as long as the governing equation is applicable to multiple locations and conditions, then you can take that information in order to correct your model prediction at other locations or other conditions. So that's the route we have taken, and we have a series of papers that have been coming out in these years.
Yeah, I might just, to your first question, Kostas, I think I 100% agree with everything Maha said. Nothing I can add there, in my opinion. I mean, the second question about model bias, in my experience, that is the worst source of uncertainty in the decision, in that it's the one that leads to the biggest problems often in the posterior estimations or information. And I mean, there are frameworks for dealing with it, such as the Kennedy-O'Hagan framework, but the challenge remains what Maha basically said, is that you have limited areas where you can implement like a Kennedy-O'Hagan or some other process type of correction. And then you have many other high fidelity regions in your high fidelity model that you don't know, and all you can do are use sort of self-consistency checks inside the framework, or some of the kinds of things that Maha's talking about, building internal structures to try to figure out how to accommodate the model bias in regions that you don't directly measure. But anyway, I'm not really adding much to the answer.
Yeah, thank you both. Thank you. This is very interesting, and I agree. The model bias is a very important issue, and to what you mentioned, the other problem in probabilistic models, right? I mean, we have so many levels of, we have a few realizations, so we need some moments or some other metrics to see the model bias, and those have their own uncertainty of the estimation. Yes. So, how will we even know that, it's biased, or is setting to the confidence intervals that we expect?
Well, this goes back to I think it's somebody in one talk earlier mentioned something, the philosophy of Occam's razor. Never use a model that's any more complex than you need, right? And that actually is important for Maha's comment, extremely important about time horizon. What are you asking your model to do, and what are the constraints you have in your decision space on when you have to make those decisions? And those are the kinds of things that should feed the answer to the complexity of the model that you want to implement.
Thank you.
I see that there was a question in the Q&A. There was first question, I think it was somebody asked, regarding the helicopter example, have you also optimized fuel consumption or other operational costs? So we put, thanks for that question. Actually, we put the fuel consumption in the constraint of that optimization, where we say we have this much amount of fuel, And so how do we make sure that we complete the mission safely within that available fuel? We also have a amount of time available to complete that mission. So all those things come under constraint for us. In terms of the optimization objective, it is basically to minimize the damage growth during the mission.
Yes. And maybe another question is also since you go into the Q&A and is related, or is for Mike, asking, can the approach be extended to components with multiple competing modes of failure or multiple modes of failure?
Yeah, so I guess the quick answer to that is, of course, the complexity there might come up if those multiple or competing influences of modes of failure rather have correlation, strong correlation between them. And this relates to Elaine's question that for me earlier, and that is, let's take stress corrosion cracking, for example. That there you have some competing physical influences, which maybe a correlated model is not available, even empirically. So that would be a challenge. But if the failure modes are just independent, maybe you can build a simplified, like the failure forecast method model, and just run them simultaneously on common data sets. And so the answer would be yes, you could do that.
And maybe a follow-up question for Professor Todd from the Q&A also, whether you can integrate synergistic effects of degradation and extreme events into the framework that you presented.
Okay, so I think I'm going to interpret that question as more about timescales. Degradation is thought of as a slow, steady, perhaps process with long-term time on the degradation, whereas an extreme event is a sudden, instantaneous, maybe low probability, but high consequence change in the inputs or demands that cause degradation to suddenly accelerate. And again, the answer is yes. I mean, if your method only is relying upon physical understanding of one type of mechanism, like the failure forecast method would very likely fail as any approach if there were not relatively, if the loading were suddenly subject to something that were many orders of magnitude or standard deviations away from some normal demand. I think it would fail because the time frame, it would suddenly fail before you had collected any data. And your prediction model is predicated upon the slow degradation or self-accelerating behavior of the cracks. So you would need to build that into your phenomenological model, like what would happen to your self-acceleration if you suddenly had an overload. And so the answer is still yes, but the current way that I was modeling would not do well to have a low probability, high consequence event like an earthquake, say, on the structure.
Maybe if I may come back one more time to this question of bias, which I think is very important. No? To what degree, I mean, if we look at a single individual system, it's very hard to understand whether there is a bias or not in our models. And if you know, of course, you can correct. But to what degree can we, when we now collect a lot of data, we develop these digital twins, not just for one individual ship or aircraft, we develop it for a fleet, and they're all different, but to what degree can we learn from the population?
Yeah.
So, and to what degree is this actually already considered in the applications that you're working on?
Yeah, this is actually a very important question, Daniel. And in fact, we have a paper just coming out on this in this Journal of Computational Physics, talking about this, where you have data, let's say, on some systems, what we call the test configuration. We have some, and then now we are trying to apply this information to a completely different system which has not been measured or tested. How do we extrapolate from all the available data, or take credit for the available data? So this is where this idea I was talking about earlier, what applies in the case of an individual system, where you take the discrepancy and then go back to the governing equation. So as long as this class of systems are all are able to use the same governing differential equation to describe their behavior, you are able to, this is why I'm saying, so we would not just quantify the discrepancy at the output or the measurement point, but we will take that information all the way to the governing differential equation, which then gets applied to other untested configurations, or unmeasured configurations and locations and conditions. So that's really the key, going back to the governing equation rather than just at the measurement point.
This was actually a very nice pass on to the next tandem series we're hosting, where I think Keith Warden might actually touch on the topic of population-based SHM. And so this would be nice to see in the context of what you described also today. I suspect a lot will depend on the parameterization of the system, which I guess is an important aspect of the twin in any event.
Yeah.
Yeah.
So there was another question that I see somebody asked. Somebody said, I think, asked about building digital twins in parallel for different components. Where I can't find it.
Yes,
yeah, multiple parallel systems and networks for different components, and then can we stitch it together? So you know, a digital twin is not just a physics model that is getting updated. It can also include things like unions and intersections. So it can, you know, that's so digital twin can also be a probability integration model, which is where the Bayesian network is a very natural vehicle for doing this, because a Bayesian network can obviously incorporate all these probability relationships and conditional probabilities. So yes, you could build. In fact, that was something we had demonstrated in a SEMI paper on where you build what we call the hierarchical building of Bayesian networks for, you know, individual components, and then pulling them together through unions and intersections. So that is possible.
There's also one question which popped up in the Q&A from a previous speaker in the series also. Professor Mongelis is asking whether it could be useful to use the value information analysis to find a balance between the accuracy of the models and the amount of data or measurement points to support a specific decision problem, also accounting for the horizon of the decision.
Yes. Find a balance between accuracy of models and the amount of data. Yes. Definitely. In fact, for that reason, I really enjoyed last week's Mateo's talk on value of information. It was, it really addressed this issue of you're getting information in models and all that. What is the value of information being provided by these different sources in supporting your decision?
Also, the talk by Maria Pina and Sebastian touched on this topic, which you might have missed. But Sebastian is here as one of the panelists, so maybe he could comment on this if he wishes.
Yeah, I mean, I can say very briefly myself that I think because VOI essentially maps everything in the process to a cost metric, to a unique metric, it's a very natural framework for doing lots of optimization problems, similar to what Maria Pina was talking about. It's very, I've not, the time horizon can also be mapped to a consequence cost. So I think it's a natural framework to do this kind of thing.
And if I may ask myself a question, for Professor Mahadevan, who showed all these very nice applications in practice. So if I understood correctly, your message is that the community is more ahead in terms of algorithms than it is in terms of measuring technology, right? Or is that?
That's true. I mean, you know, computational algorithms, which is what our community does a lot. So yeah, we are far more advanced in the computational algorithms, but not so much in terms of the infrastructure to support them. Yeah.
I see Mike nodding, so I think he agrees. Okay.
Yeah. What about the infrastructure, or how prepared are actually the companies and to actually use this in an integrative manner?
Yeah.
I mean, you work with some of the, let's say, top kind of players that I guess are most advanced. I mean, you sometimes work with players that are a bit less advanced, and it's not always so easy to actually, you know, make them integrate such even if we would have them, such technology into their operations.
So a very funny thing is happening. So some of the smaller companies, they are certainly nowhere near this level of sophistication that we talk about, you know, in our academic circles in terms of building digital twins. But you go and search on the internet, you will find thousands of small companies that are marketing digital twin services. They're saying, oh, we have a digital twin for you. All they have, in fact, I went and dug into this. All they have is maybe a finite element model, some simple computational model, input-output model, and they are just packaging it as digital twin. So there is a lot of that going on, where there is, you know, marketing but not actual substance. But even the bigger companies are realizing that the digital twin is easier said than done. So there is a long-term sustained investment that they have to make in order to make it a reality. And so even in bigger companies, it has not gone very far. It is moving slowly.
I mean, I think the best opportunity to convince any customer, big or small, about implementing such a strategy is to find something that has a relatively low consequence cost associated with the process, and then you can condition them on that and they'll trust the process to do more important decisions. That's what we found with the US Army I know Maha's also worked with the US Army, but we found helping them make some low consequence maintenance decisions with a digital twin architecture similar to what Maha's talking about allowed them to buy the confidence in us for a little more consequential decision making.
Yeah.
Okay.
Maybe
you have. Oh, sorry.
I was going to say that we have somewhat exceeded our time, so maybe we could wrap it up, at least for the formal part of the session. We typically ask our speakers to give us a closing statement. So what do you want to leave the audience with? And maybe Mike could start as the first speaker of today. Caught him by surprise.
Well, yeah, I mean, I think this idea of quantifying rigorously the uncertainty in our prognostic process is the most important, lowest hanging fruit that we can take from you know, the hierarchy of things we could do in prognostics. Physics is hard, it's long term. I agree with Daniel, if we knew all the physics, that's fantastic, that's the end. We also don't have enough data yet for the whole life cycle. So I think it's this idea of really strong low order models with really well quantified uncertainty that will be the fastest way to make progress.
Mm-hmm. And for Maha?
Yeah, this is, we are all in a very fertile field, which I think will go for quite a while. And this is actually a pretty exciting time where you have sensing technologies being advanced, computational power, intense computational power, the internet advancements, and uncertainty quantification. So all these things coming together, it's actually, from a technical point of view, it's very exciting. But practical implementation is going to take quite a few years. So I think we are all in for a productive time for a long time to come.
All right. So let's get going and go to work.
Sounds good.
Yes. Thanks again, I think, from my side for the great and excellent talks and for the willingness to participate in the discussion. I think it was very insightful and I also learned a lot.
Many thanks. All the best to everybody. Yeah.
Thank you for inviting us. Yeah.
Thank you
Yeah,
for
thank
the
you very
audience
much.
and panelists as well. Yes. Have a nice day, everyone.
I noticed that at some point that